Hello and welcome to Engineers Mindset Academy. So in the previous videos, we've done first order differential equation using the idea of Laplace transformation. In this video, we are going to be continuing with second order differential equation using the idea of Laplace transformation. Now we have a question on the board. Before going into this question, let's first of all do a revision on what we've learned so far on applying Laplace transformation to solving differential equations. Now, I said that there are 4 key steps to employ when utilizing Laplace transformation to solve differential equations. The first step always is to write the Laplace transformation of all the functions involved in the differential equation. That's the first step. The second step is to impute the initial conditions given in the differential equation. The third step is to rearrange the equations to obtain the Laplace solution of the differential equation. And after that, then you take the Laplace inverse of the given function. That becomes the final step. Now, before carrying out this 4 steps to solve this problem, let's do a review. I said in the previous videos that while solving differential equation problems using Laplace transformation, first thing to note is always dy all over the s from the initial condition is always taken as s1. Also, I said the squared y all over the s squared is always taken as s2, and the cube y all over the s cube is always taken as s3. So it continues in that order. Okay, the next thing to also consider is the Laplace transformation of s. I said it is always taken as what? S bar. Okay, next is Laplace transformation of dy all over the s. This is always taken as s times s bar minus s naught. Sorry. Also, I said the Laplace transformation of the squared y all over the x squared is now taken as, since this is the squared y over the x squared, it becomes s squared times s bar minus, now this s has to reduce to 1, so it becomes s times s naught minus, okay, now I'm exhausting s, so s has to be s to the power of 0, which remains 1, so I'm left with what? S1. So it continues. If I have a third order differential equation, then the Laplace transformation of the cube y all over the s cube is simply equal to, this becomes now, since this is third order, I have x to the power of 3 times x bar, okay, minus, now this s reduces, it becomes s to the power of 2 times x naught, and again this s reduces, it becomes x, okay, s times x 1, okay, then this s now is to the power of 0, which becomes 1, then I have minus s2. So the idea continues like that. It means if I have fourth order, then the Laplace transformation of the fourth y all over the x fourth is now going to be equal to, see the same thing now, I start with s to the power of 4, always 4 order, multiplying by what? X bar, minus, now s drops by what? 1, it becomes s to the power of 3, in this case now, times s naught. Then it continues, s drops by 1, it becomes s to the power of 2, now times s1. S also drops by 1, it becomes s, now times s2. Finally, s drops by 1 again, it becomes s to the power of 0, which is 1. So 1 times, I have here s3 left. So this is how you solve your differential equation, different order differential equation. Now in this case, I have a second order differential equation given the squared y all over the x squared, okay, minus 6 dy dx minus 6 dy dx plus 8s to be equal to exponential to t. Now the first idea or the first thing to do when using Laplace transformation to solve differential equation is always write the Laplace transformation of all the function. Okay, so you have to rewrite the equation by using their Laplace transformation. Okay, so that means I'll have Laplace transformation of the squared y all over the x squared minus, now this is a constant 6, we'll pull it out, 6 Laplace transformation of the y all over the x plus 8 is also a constant, pull it out, it becomes 8 Laplace transformation. Now I have just x here, and this is equal to the Laplace transformation of exponential to t. All right, you have this. So all we need to do now is to what? Rewrite the Laplace transformation of each of these functions. That's the first step. Now we've said what is the Laplace transformation of the squared y over the x squared, which is what I explained earlier here. This is the Laplace transform of the squared y over the x squared. So you put this down. In place of this, I have x squared times x bar minus x naught minus x1. So this is for the first case, Laplace transformation of the squared y over the x squared minus 6 times Laplace of the y over the x. So I simply said Laplace of the y over the x is taken as x bar minus x naught. So in place of the y the x, we have x bar minus x naught, okay, plus 8 Laplace of x. And I said earlier, the Laplace of x is always taken as what? S bar. So you append that there, this becomes 8s bar. And this is equal to, we have the Laplace of exponential 2t, okay, and I said in the table of standard values, the very first 3 videos we did on introduction to Laplace transformation, I said in the table of standard values, Laplace of exponential at is always taken as 1 all over s minus a, where a is a constant, which is the power of the exponential function. Therefore, if we are seeing Laplace of exponential 2t, automatically this is equal to what? 1 all over s minus 2. So this is among the table of standard values. You don't need to solve, you just need to know them. So the Laplace of exponential 2t is simply 1 all over x minus 2. Hence, in place of this, we have 1 all over s minus 2 in place of Laplace of exponential 2t. Now, having this, the next thing to do is to what? Let's expand the brackets. Okay, so I have here x squared times x bar minus s naught minus s1, okay, minus 6 times xs bar gives me 6s bar, minus times minus here becomes plus 6 times x naught, okay, plus 8s bar, and this is equal to 1 all over x minus 2. We have this. Now, the next thing to do, the second condition says, after rewriting the Laplace transformation of the functions, the second condition says, impute now the initial conditions. And from the question, it says, when t is equal to 0, x is equal to 0, dy dx is equal to 5. Now, you have to be very careful with this. When t is equal to 0, x, I did this in the first video on utilizing Laplace transformation to solve differential equation. I explained all of this in that introduction video, and I said if t is equal to 0, x is always taken as what? X naught. X is always taken as s naught. So which means if x is equal to 0, automatically s naught is equal to what? 0. Now we have dy all over the x, and I explained earlier that when solving Laplace transformation, dy dx is always taken as what? X1. The squared y over the x squared is always taken as x2. The cube y over the x cube is always taken as x3, and so on. So which means I have dy all over the x here. This is simply equal to what? X1, and x1 is simply given as what? 5. So these are the initial conditions given to us. When t is equal to 0, x naught is equal to 0, x1 is equal to 5. So we simply plug in these conditions into the equation. That's the second step. So I have x squared times x bar minus, I'm seeing x naught. So this is now x times, what is x naught? X naught is equal to 0. So it becomes x times 0 minus x1. What is x1? X1 is equal to 5. So you put it down, 5 minus 6x x bar plus 6x naught. Again, x naught is equal to 0. So it becomes 6 times 0 plus 8x bar, and this is equal to 1 all over x minus 2. You have this. So let's evaluate now. This is now x squared times x bar minus x times 0 is off 0. I'm left here with minus 5 minus 6x bar, 6x bar plus 6 times 0 is 0. That's off. So I'm left with plus 8x bar. And this is equal to 1 all over x minus 2. Okay. Now we can factorize. I have x bar here. I have x bar here. I also have x bar here. So which means we can actually factorize x bar between these three. So we simply sum them up now. I have x squared This is minus 6x, and this is plus 8. All of them multiplying by s bar, okay, minus 5, and this is equal to 1 all over s minus 2. We have this. The next thing now to do, the third condition says, rewrite the equation to obtain the solution, the Laplace solution of the differential equation. And the Laplace solution of the differential equation is what? X bar. Remember we said Laplace of x is simply what? X bar. So which means we have to make x bar subject of the formula. This is the Laplace solution of this differential equation. So which means in order to make x bar subject, first thing to do is to what? Send minus 5 over to this side of the equation. So I have x squared minus 6x plus 8 multiplied by s bar, and this is equal to 1 all over s minus 2. If minus 5 cross an equal to sign, it becomes plus 5. So we simply have this. All right. So I think I can wipe here now. Okay. So from here, in order to make x bar subject, it means I have to divide all through by x squared minus 6x plus 8. In order to make x bar subject, I have to divide all through by this coefficient x squared minus 6x plus 8. Therefore, x bar is now equal to, now on this side I have 1 all over x minus 2. It becomes 1 all over s minus 2. Now if I'm dividing through by that, by this value, I will simply have here x squared minus 6x plus 8. Okay, plus 8. Okay, so I have this for this, plus, now I have 5 all over same thing, x squared minus 6x plus 8. I simply have this. So dividing all through by x squared minus 6x plus 8, that simply makes x bar subject of the formula. Now the final condition, which is the fourth, simply says to obtain the Laplace transformation of the solution, all you need to do is to what? Take the Laplace inverse of the solution, and that will give you the solution to the differential equation. So all we need to do now is take Laplace inverse of x bar. That simply means taking Laplace inverse of these individual functions here. So I have Laplace inverse of 1 all over x minus 2, x squared minus 6s plus 8. Okay, plus the Laplace inverse of 5 all over x squared minus 6s plus 8. So we simply take the Laplace inverse of each of these functions. So the Laplace inverse of x bar, remember, if the Laplace of x is equal to x bar, then it means that the Laplace inverse, taking the inverse of x bar, will give me backwards x, which is the original solution. So Laplace inverse of x bar automatically gives me what? X, which is the solution of the differential equation. So keeping that in mind. All right. Our major problem now is to find the Laplace inverse of this and Laplace inverse of this. So let's pick them individually and solve. Let's simply call this equation 1. Let's call this equation 1. Then from equation 1, Laplace inverse of x bar automatically is equal to x. This is settled. The next thing now, let's solve for the Laplace inverse of 1 all over s minus 2 times x squared minus 6x plus 8. Let's find the Laplace inverse of this function. Alright, so before looking for the Laplace inverse of this function, let us first of all solve for this function. Since this is a compound fraction, then we have to first of all use the method of partial fraction to break this compound fraction into two simple fractions before we can use the Laplace inverse theorem to solve. Because at this point like this, you cannot be able to solve the Laplace inverse of this function. So the very first thing to do is to what? Break this function into what? Using partial fraction into two simple fractions, then we cannot find their Laplace inverse. Therefore, 1 all over s minus 2 into x squared minus 6s plus 8 is now equal to, so we simply break this using partial fraction. But before doing that, let's first of all look at the denominator of this function, x squared minus 6s plus 8. Can this be factorizable? That's the first thing to do. X squared minus 6s plus 8. What are two numbers such that when you multiply these two numbers, you're going to have plus 8. But when you add them together, you're going to have minus 6. Obviously, the two numbers are minus 2 and minus 4, such that minus 2 times minus 4, minus times minus is plus, so you have plus 2 times 4 gives you what? 8. Again, when you add minus 2 plus minus 4, you're simply going to have what? Minus 6, which is the middle term. So it simply means that the factor of this quadratic equation are what? Minus 2 and minus 4. Therefore, you can simply write this equation as what? It becomes s minus 2 times s minus 4. Simply because if you expand this, you're going to obtain this. The factors are minus 2 and minus 4. So x times x gives you x squared. X times minus 4, that's minus 4x. Minus 2 times x gives you minus 2x. And if you add them both, you have minus 6x. And so on. So simply, if you expand this, you're going to be obtaining what? This function here, or this quadratic equation. So it means that we can actually break this down further into x minus 2 and x minus 4. So we can now rewrite that equation. This is now equal to 1 all over, I have s minus 2 times, I have s minus 2 times, I have s minus 4. Okay, so this can now be written as that. Let me take care of. Now you observe that at the denominator I have x minus 2 times x minus 2, so which means these two factors are the same. So this is now equal to 1 all over x minus 2 multiplies x minus 2 will give us x minus 2 all squared times x minus 4. Alright, so this whole term has been broken down into this. So let's now use partial fraction to analyze this. So I have 1 all over x minus 2 all squared times x minus 4. This is equivalent to, by partial fraction, now I have a all over, when I have, or when I see x minus 2 to the power of squared, it simply means repeated linear factor as the denominator. Okay, so which means how to approach it simply is going to be x minus 2 plus b all over x minus 2 all squared, because we have a factor that is repeating as the denominator, x minus 2 all squared. So it is repeated linear factor, and this is how you solve it. All right, so plus c all over the final bracket there, which is s minus 4. All right, so we have this. The next thing to do now is collect LCM. Now, you may want to use the cover-up approach to solve this problem, but using the cover-up approach will only give you a result for C, and which is not what we want. We want to solve everything at once. So the first thing to do is, in this case now, since I have repeated linear factor as denominator, which means I have to automatically take my LCM. So let's take the LCM. This becomes 1 all over x minus 2 all squared times s minus 4. And this is equivalent to, let's take LCM on this side. The LCM still remains s minus 2 all squared multiplies x minus 4. This remains the LCM. Now, the whole of this divide by x minus 2. X minus 2 cancels one of these x minus 2. I'm left with x minus 2 here times x minus 4. So this becomes a times x minus 2 times x minus 4. Using this to divide x minus 2, okay, this bracket. The next is to use this denominator now, or this LCM now, to divide x minus 2 all squared. Notice that the squared, x minus 2 squared cancels x minus 2 squared, so I'm left with what? X minus 4. Use that value to multiply b. This is now plus b times x minus 4. Okay, plus same thing, use the LCM to divide x minus 4. Alright, so x minus 4 cancels x minus 4. I'm left with c times x minus 2 all squared. You have this. All right, so from the principle of partial fraction, if the denominators are the same, then it means the numerator must be identical. From the principle of partial fraction, if the denominators are identical, it also means that the numerator must be identical. So if I look at that question, or that last set we solved now, notice that on both the left-hand side and the right-hand side of the equation, the denominators are the same. You have x minus 2 all squared multiplying x minus 4. So since they are the same, it simply means that their numerators must be what? identical. Since their denominators are identical, numerators must be identical. Hence, at the numerator, I have 1 is equivalent to, this is A times x minus 2 times x minus 4 plus B times x minus 4 plus C times x minus 2 all squared. We have something like this. Now let's use the substitution approach to determine the values of B and C first, then we can fall back to this equation. So let's simply call this equation 2. Remember we had an equation 1 earlier over here. Alright, so to find B, in order to find B, using substitution approach, you look at what is in the bracket of the other terms, the common factor in the bracket of the other terms. I have x minus 2 in A. I also have x minus 2 in A. So choose the opposite of the number in that bracket as a value for x. That will help nullify the effect of the other terms in the bracket. So I have x minus 2. Minus 2 is a number. Opposite of minus 2 becomes what? Plus 2. So I'm going to consider x to be what? Plus 2. So such that if I put plus 2 here, it becomes 2 minus 2, which becomes 0. So automatically A is cancelled. Same thing happens here. 2 minus 2 becomes 0. So C is cancelled. Then I can find the value of B. So to find B, simply say let S be equal to 2. So put that into this equation. I have 1 to now be equivalent to, this is A into, in place of x, this is x minus 2 and x is 2. This becomes 2 minus 2 times x minus 4. X is 2, so it becomes 2 minus 4 plus B into x minus 4. X is 2 minus 4 plus C into x minus 2 all squared, and x is 2. It becomes 2 minus 2 all squared. Okay, so 1 is now equivalent to, mind you, 2 minus 2 is 0, 0 times A is 0, 0 times everything here is 0, so this is off. Similarly, 2 minus 4 here is minus 2, minus 2 times B gives us minus 2B. And here I have 2 minus 2 is 0, 0 times, or 0 squared is 0 times C is 0, so that's off. Hence, D is equal to what? It becomes minus 1 all over 2. Simply dividing through by what? Minus 2. That gives us B. Same thing now. To find C, you look between A and B. What is the common term in the bracket? I have x minus 4 in A. I have x minus 4 in B. So which means I can simply take the opposite of this number, minus 4, in this bracket, and put it in place of x. So the opposite of minus 4 is simply plus 4. So if I call x to be plus 4, automatically it becomes 4 minus 4, which is 0, hence B is off. I also have here 4 minus 4, which is 0, hence A is off. And that will help me to find what? C. Alright, so to find C, simply set or let S be equal to what? 4. Therefore, in this equation I have 1 is now equivalent to, this is A into S minus 2, and S is 4 minus 2 times S minus 4. S is 4 minus 4 plus B into S minus 4, and S is 4. So you have 4 minus 4 plus C into X minus 2, and X is 4. 4 minus 2 all squared. You have this. 1 is equivalent to, mind you now, 4 minus 4 is 0. 0 times 4 minus 2 times A, everything here becomes 0. 4 minus 4 is also 0. 0 times B becomes 0. 0. Finally, I have 4 minus 2 is 2. 2 squared is 4. 4 times C gives us 4C. So this simply implies that C itself is equal to, simply divide through by what? 4. I have 1 divided by 4. Alright, so this gives me the value of C. Now, I've gotten B and I've gotten C. Notice that we cannot use the substitution method to find A, simply because A contains what? X minus 2 and x minus 4. So we can't use the substitution method to solve. That will bring us to what? Expanding this function. Okay, so we have to now expand this given function and solve. Since we already know the values of B and C, we simply expand the function and solve for A. Therefore, from this equation now, I'll have that 1 is equivalent. Let's now expand. This is A into S times X will give us X all squared. X times minus 4 will give us minus 4S minus 2 times x will give us minus 2 times x, minus 2 times minus 4 gives us plus 8. Okay, plus b times x gives us bs, minus b times 4 gives us 4b. Okay, plus c. All right, so let's expand x minus 2 all squared. So we simply have x minus 2 times x minus 2. This will give us x minus 2 all squared. So x times x gives us x squared. X times minus 2 gives us minus 2s. Minus 2 times x also minus 2s. Minus 2 times minus 2 gives us plus 4. All right, so we have this for that. Okay, so 1 is equivalent to, okay, a into x squared minus 4x minus 2x is minus 6x, so I have minus 6x plus 8 plus bs minus 4b minus c into plus c into, this is x squared minus 2s gives us minus 4s plus 4. All right, we have this. So let's expand the brackets now. 1 is equivalent to a times x squared gives us ax all squared minus a times 6x gives us 6as plus a times 8 gives us 8a plus bs minus 4b plus c times x squared gives us cx all squared minus c times 4x gives us 4cs plus c times 4 gives us 4c. All right, so let's compare coefficients now. 1 is equivalent to, let's bring all the terms containing x squared. I have a x squared here, and I have plus c x squared. So a plus c times x all squared. Okay, let's bring all the terms containing x. I have minus 6a x, I have plus bs, and I have minus 4cs. So let's add them all. This is now plus. Let's start with bs. This is now b minus 6a, okay, minus 4c, all multiplying by s. Finally, let's pick the constant term. I have plus 8a here is a constant, plus 8a. I have minus 4b, minus 4b. I have minus 4c, okay, plus 4c rather, plus 4c over here, and those are the constant terms. So these are terms with x squared, these are terms with x, and these are the constant terms. So with this now, we can find the value of a using comparing coefficients. So we can either compare x squared, we can compare x, we can compare the constant term, and I think the easier one here is to compare x squared, since I have a plus c multiplying x squared. So simply compare. On the left hand side, there's no term that contains x squared, so automatically a plus c becomes equal to 0. Okay, let's do that here. So by comparing coefficient now, I only have the constant term 1 on the left hand side of the equation. There is no term that contains x squared on the left hand side. So which means comparing x squared, coefficient of x squared, it means a plus c is equal to what? 0. Therefore, for x squared, this simply implies that a plus c is equal to 0. But what is c? C is 1 over 4. So this simply implies that a plus, in place of c, c is 1 all over 4, and this is equal to 0. Therefore, to make a subject, simply send 1 over 4 over here, and this simply implies that a itself is now plus 1 over 4, cross and equal to sign becomes minus 1 divided by 4. So we have the values now of all the constants. Okay, so having obtained the values of the constants, then we can now plug them into the equation. Remember, it was 1 all over x minus 2 times x squared minus 6x plus 8 that gave rise to 1 all over x minus 2 all squared times x minus 4. Not forgetting, it was this that gave rise to this from what we were solving. And this is now equal to, remember, we said this is equivalent to what? a over x minus 2, let's put it out. We said it's equivalent to a over x minus 2 plus b all over x minus 2 all squared plus c all over x minus 4. Now we know the values of a, b, and c. Let's now plug them into this equation. All right. So 1 all over x minus 2 times x squared minus 6x plus 8 is now equivalent to, so we said a over x minus 2, and what is a? We just obtain a as minus 1 all over 4, so we have minus 1 all over 4 into x minus 2, so times x minus 2. Okay, plus b, and what is b? B is minus 1 over 2, so this becomes minus 1 all over 2 into x minus 2 all squared. I have x minus 2 all squared plus c, and what is c? C is equal to 1 all over 4, so this is plus 1 all over 4 into x minus 4. You simply have this. Therefore, the partial fraction of that given compound fraction has been obtained as that result on the right hand side of the equation. So we can now find the Laplace inverse of the given functions. Let's now find the Laplace inverse. So remember, what we are looking for is Laplace inverse of 1 over x minus 2 times x squared minus 6x plus 8. It is simply the Laplace inverse of this function we are looking for. Therefore, the Laplace inverse of 1 all over x minus 2 into x squared minus 6x plus 8 automatically becomes now the Laplace inverse of minus 1 all over 4 into x minus 2, okay, minus 1 all over 2, okay, you can simply take them individually, minus Laplace inverse of 1 all over 2 into x minus 2 squared, okay, plus the Laplace inverse of 1 all over 4 into x minus 4. You can take them individually in this manner. So this is equal to, let's pull out all the constants. Minus 1 over 4 is a constant. Pull it out of the Laplace sign. It becomes minus 1 all over 4, the Laplace inverse of 1 all over x minus 2. Okay, minus also minus 1 over 2 here is also a constant. Pull it out. Minus 1 all over 2 Laplace inverse of 1 over x minus 2 all squared. Okay, plus 1 over 4 is also a constant. Pull it out. Plus 1 over 4 Laplace inverse of 1 all over x minus 4. Okay, so let's obtain the Laplace inverse of these values. All right, so from the table of standard values, we've explained that, I think I can wipe here now. All right, so from the table of standard values, we've explained that the Laplace transformation of exponential at is equal to 1 all over x minus a, where a is a constant. Okay, so this simply means that if I'm asked to find a Laplace inverse of 1 over x minus a, automatically this becomes what? Exponential at, taking it back to the original equation. Hence, the Laplace transformation of exponential 2t becomes now 1 all over x minus a, and a in this case is 2. It becomes x minus 2, which means that the Laplace inverse of 1 all over x minus 2 will take us back to what? The original equation, which is exponential 2t in this case. So considering that now, we are going to be having the Laplace inverse of 1 all over x minus 2 times x squared minus 6x plus 8 to now be equal to, this is 1 over x minus 2, and the Laplace inverse of 1 over x minus 2 remains what? Exponential 2t. Remember, there is minus 1 over 4 attached to it, so this becomes minus 1 all over 4 exponential 2t minus 1 all over 2. Now, mind you, from the table of standard value, we've already explained the Laplace inverse of 1 over x minus 2, when it is carrying now a square, automatically this becomes t exponential 2 t. So the Laplace inverse of 1 over x minus 2 all squared is simply t exponential 2t. Okay, plus 1 all over 4. Laplace inverse of 1 over x minus 4 gives us exponential 4t. So the Laplace inverse of this function is simply what? Equal to this. So we've gotten this particular one from equation 1. We'll find this side. Next is to find the Laplace inverse of 5 over x squared minus 6x plus a. So we don't really need to solve much for this, since we already obtained something relevant to it. We can use the idea we've already solved here for this particular one. Okay. So the first part of the equation is solved, which is this. The second part now is to find the Laplace inverse of 5 all over x squared minus 6x plus 8. So we simply find the simple fractions of that compound fraction. We have x squared minus 6x plus 8, and this is equivalent. We've already done this towards 5 all over, writing this into in terms of their factors. This is x minus 2 multiply x minus 4. Okay, x minus 2 times x minus 4 will give us x squared minus 6x plus 8. We've already explained all of this, so which means this will be equivalent to we have a all over x minus 2 plus b all over x minus 4. In this case now, you can employ the cover up method to solve. To find a, I'm simply going to cover up what? X minus 2. So simply cover up x minus 2 from this equation. Hence, cover up s minus 2. So this will help us to find a. Alright, so a is now equal to the limit as s tends to 2. Remember, I'm covering up x minus 2. So I'm considering limit as s tends to 2 into this equation 5 all over. Now I'm covering up x minus 2, so I'm left with x minus 4. Now this is equal to 5 all over. X is now 2. So you have 2 minus 4. And this is equal to 5 all over. 2 minus 4 is minus 2. And this will give us minus 2.5. That means A, this simply implies that A is equal to minus 2.5. Alright, we have this. Next up now, to find B, simply cover up what? Simply cover up x minus 4. Okay, so to find B, you cover up x minus 4. Therefore, to find B, cover up s minus 4. Hence, B becomes now the limit as s tends to 4 of the function 5 all over. Now is going to be x minus 2. Okay, so I'm covering up x minus 4, so I'm left with what? 5 over x minus 2. Okay, so this is equal to 5 all over. Putting in the limit now, x to be 4. It becomes, in place of x, I have 4 minus 2, which is 5 all over 2. 4 minus 2 is 2, and 5 divided by 2 gives us 2.5. So this simply implies that B itself is 2.5. So A is minus 2.5 and B is 2.5. Alright, so having found this now, alright, so the compound fraction 5 all over x squared minus 6x plus 8 is now equivalent to, so we said it is equivalent to 5 over x minus 2 times x minus 4, which is equivalent to a all over x minus 2 plus b over x minus 4. Now we know the value of a is minus 2.5, so this is now equivalent to minus 2.5 all over x minus 2 plus b, okay, b over x minus 4, and b is equal to 2.5, so plus 2.5 all over x minus 4. Therefore, the Laplace inverse of this function 5 over x squared minus 6x plus 8 is now equal to the Laplace inverse of this individual function minus 2.5 all over x minus 2 plus the Laplace inverse of 2.5 over x minus 4. Okay, so let's continue over here. So this means the Laplace inverse of 5 all over x squared minus 6x plus 8 is now equal to, as usual, let's pull out all the constants. So I have minus 2.5 Laplace inverse of 1 over x minus 2 plus 2.5 Laplace inverse of 1 over x minus 4. Okay, now this is equal to, as earlier said, the Laplace inverse of 1 over x minus 2 becomes exponential 2t. Hence, we have minus 2.5 exponential 2t plus 2.5. Same thing here, Laplace inverse of x minus 4 becomes exponential 4t. We have exponential 4t. All right. So we know the Laplace inverse of this. We know the Laplace inverse of this. We can now solve into this equation or put them into this equation out, obtain the solution of the differential equation. Laplace inverse of x bar, we call that x. And this is equal to the Laplace inverse of this term. We already obtained the solution here, which is minus 1 over 4 exponential 2t minus 1 all over 4 exponential 2t minus 1 all over 2t exponential 2t, okay, plus 1 all over 4 exponential 4t. That gives us the solution to this, plus, okay, this Laplace inverse of this function which we obtained here. In this case now we have minus 2.5 exponential 2t plus 2.5 exponential 4t. All right, so let's see if you can collect like terms. All right, so I have minus 1 over 4 exponential 2t minus 2.5 exponential 2t. That will give us minus 2.75 minus 2.75 exponential 2t minus 1 all over 2 t exponential 2t, okay. I have plus 1 over 4 exponential 2t plus 2.5 exponential 4t, which will also give us plus 2.75 exponential 4t. All right, so this becomes the solution of that second order differential equation. All right, guys, so that's how you apply Laplace transformation to solve second order differential equations. Maybe in the next video, I will see you with a couple of examples still on second order differential equation utilizing Laplace transformation. Till then, stay safe. I'll see you in the next video. Thanks. Cheers.